ball, Bernardo. Connect my device. And this good dog, some toys. All right. Yeah, it looks like 6 students. All right, how many we got? 7 students now. Wait another minute or two.
Dr. Small, I had a question.
Sure.
For fall, when we go to in-person classes, are we going to be required to be wearing masks at all times?
That is the only thing I am quite certain of, that they will require you to wear masks.
Okay, good. That's what I was wondering. That's good.
I have no idea. They're going to probably several times change the rules on how people sit. I've been asked questions like, will people be, let's say you have a Zoom class at 10 a.m. and an in-person class at 11. Could you sit in the library with your laptop at 10 a.m.? I'm pretty sure the answer will be yes, but they'll have rules on capacity and spacing. Then those rules will either result in enough people that someone panics and complains, or too few people and students need to go somewhere. So then the rules will change. Then they'll change again. Then they'll change yet another time. Then everyone will ignore them. Then there'll be yet another change. Then they'll yell at the professors and tell us it's our fault. So I'm quite certain that that will get screwed up. I'm quite certain that they'll change the rules on how and where you sit and what you can and cannot do and what we can and cannot do in lab, but they will require masks. That I'm certain of. I'm completely certain of that. I'm also certain that they will require masks in 2022 and probably 2023. And the people who will tell us to wear masks will all be people who, like me, got vaccinated and like me say that they believe that vaccines work. And then they'll tell us the vaccines don't work. And I'm going to be like, wait, Jesus Christ, did they replace the campus administration with Jenny McCarthy and RFK Jr.? Because vaccines work. But anyway, so, we got that to look forward to.
And for recitations, you know how we do a lot of group work? Are we going to be allowed to even work in groups for that?
Well, you won't be touching things together. I mean, you all have your own worksheets. You'll sit a certain distance apart. And look, just get the damn vaccine. It works. But yeah, I mean, people will be spaced out. But the best answer to all of this is just get the damn vaccine because it's free and it works. So yeah, get the vaccine, get the vaccine, get the vaccine. That's my answer to everything. That and the administration will screw things up. Those are the two certainties in life. We know that vaccines work and we know that the administration will screw things up.
I'm not looking forward to the second one, but that sounds good.
Anything else about fall or whatever?
Professor, I have a question. So what about office hours and like the lines to like Panda Express and stuff like that?
The rules will change several times. The good news for office hours is that we've all learned how to use Zoom. But look, get the vaccine because vaccines work. So if you get the vaccine, you're safe. And then we just wait for some administrators to realize, oh yeah, vaccines work. I wish we'd figured that out like a century or so ago. If only we had a college of, like a certain kind of scholar that studies the natural world and technology and how does it work. It begins with an S. I can't remember what it is. Psychology, psychics, I don't know, something. Science. Yeah, if we had a college of science, then we would know the vaccines work. But we're going to spend a bunch of time pretending that we don't know that vaccines work. But just get the damn vaccine and you don't have to worry about Panda Express or office hours. You can just go because vaccines work. Anything else? I mean, look, inoculation is one of those things. Modern vaccines are, well, modern. But the idea of inoculation goes back centuries. It was debated in colonial America. There were some people who were skeptical of it. And there were some people who were quite in favor of it. It should be no great surprise that there were actually quite a few Puritans in favor of it because the Puritans were always the smart ones among the groups of colonists that came over here. Some of the other colonists, not so bright. But the Puritans were always the smart ones. And there were a lot of Puritans who supported inoculation. The idea that exposure to certain kinds of milder illness could protect you against more severe. There were already observations going back that far, that inoculation, the exposure to a more innocuous form of a germ could protect you against something else. This was known centuries ago. And then in subsequent years, people came up with better understandings of this. And now we're at the point where we can use mRNA technology to devise a vaccine practically as soon as a virus is discovered. But vaccines work. Any question, what about office hours? What about bookstore? What about the library? What about the BSC? What about the gym? What about the whatever? My answer to what about the whatever is that vaccines work. All right, let's talk about optics now. Last time, we had finished by talking about the fact that if we have some light that crosses an interface, we know that in general, some of it is transmitted, and the transmitted light, its angle obeys Snell's law. And some of it's reflected at the same angle. And we talked about the fact that, well, for TE light, we got that the reflectance is N1 cosine theta 1 minus N2 cosine theta 2 over N1 cosine theta 1 plus N2 cosine theta 2. And so we could understand from this why higher index materials give you stronger reflection. One thing you can understand from this, or we can also understand why looking at something at a glancing angle is going to give you stronger reflection than looking at something head on. Another thing we can understand from this is mirages, okay? Now, the refractive index of air is very close to 1. But it's not exactly 1. And cold air is going to be dense, and warm air is going to be less dense. So let's say we've got asphalt, it's really warm. All the air right at the surface of the asphalt must be close to the temperature of the blazing hot asphalt. And this must be cold. So this is going to be high index, and this is going to be low index. And in reality, there are many layers, but if we just oversimplify it to get at the idea, delta n is minuscule. So head on, if you look down at the ground, basically no light reflects. You see the ground. But at grazing angles, you actually do see some amount of significant reflection. And so at grazing angles, that's basically because one of the angles are close to 90 degrees, and one of them is even closer to 90 degrees. So the cosines get really small. And you might think, well, having small numbers in the numerator doesn't help you much. No, it doesn't. We already had small numbers in the numerator, though. Now we've also got small numbers in the denominator. Those cosines, those angles are going close to 90 degrees. Those cosines are going to zero, one of them faster than the other. And so you can get a reflectance that's close to 1. And that's a mirage. And you've all seen that looking off in the distance at the layer of air above asphalt or above some other really hot surface. Any questions on that? Now that's for TE waves. That's for when the light is, when the electric field is coming out of the page. So if here's our K vector, here's our E field out of the page, and then here is our B field. For TM waves, things are more complicated. For TM waves, we got that, I'll just draw the K vector and the, now it's the magnetic field that comes out of the page, and it's the E field that's perpendicular. So it's in the page, perpendicular to both of those. For the TM waves is cosine theta 1 over N1 minus cosine theta 2 over N2. And we could go through a bunch of algebraic gymnastics, and what we would find in the end is that tan theta 1, if tan theta 1 equals 0, sorry, if tan theta 1 equals N2 over N1, then we get that R12 equals 0. And that has an interesting implication, which means that there is an angle at which all of the TM light is reflected, sorry, transmitted. Which means that all reflected light is TE. It's the other polarization. Now, there might not be a lot of reflected light, but this is a way to be absolutely certain that whatever you're getting, that this is a way to be absolutely certain that the light you're getting is polarized in a particular direction by sending in the light at Brewster's angle. Now, I say absolutely certain, but in reality, the surface is always somewhat rough and warped, and so not all of the light is being reflected at that angle. But this is a way to get very strongly polarized light by sending it in at the Brewster angle. The only problem is that while you have a great way of selecting one polarization, you look at the reflected light, the transmitted light, well, there's still plenty of TE light that gets transmitted mixed in with the TM light that gets transmitted. And we'll get to how to address that, but any questions on this concept so far? Let me tell you why we might want that. There are lots of things that could be said about polarized light, and maybe later I'll show you some pretty pictures. But one practical application is, let's suppose we have something set up so that one of these things will always pass TE and reflect. Oops, no, that it should be reflecting TE and passing TM. And then we set up the other one so that it's reflecting, we kind of orient it in a different way so that TE here, TE light, so something who's, see here, TE light would have to have a reflection that's vertical, because if the light was coming in like this, the E field will be out of the screen, okay? So we've set it up so that the E field is out of the screen. That's TE, and it'll be reflected. And the TM light will be transmitted. Now we could set up the other polarizer over here, the other reflector, so that if we've got something coming out of the screen, if I've got light with an E field coming out of the screen, that is in the direction of the reflector. So we'd have to have another reflector, which is actually going to be oriented weirdly, but I can't draw it. And we'll just say that that one is transmitting the TE light. And you could say, well, not the way this is drawn. Yeah, fine, not the way this is drawn, but I'm no good at 3D drawing. And the TM light would be reflected. So actually, you know what? I made that way harder than I needed to. Make that way, way harder than I needed to. Here too, TM light will be reflected, will be transmitted. This will work. I was going to do something funkier, but it doesn't matter. Okay. Why do we care? Because people can set up light sources that emit two photons with their polarizations opposite, where one of the photons is TE and the other one is TM, okay? So basically, if one of them has its electric field like this, the other one will have it out of the screen. And if one of them has its B field like this, I'm trying to draw perpendicular to that, the other one will have its B field going up. My dog is currently barking at the tennis ball. Okay, so why would we do that? Here's why we do that. Because in quantum mechanics, people can prepare atoms in states such that while we don't know which direction they'll emit which photon in, we know that the two photons will be opposite. So either they'll emit TE left, TM right, or they'll emit TM left, TE right. Okay, and for those of you who haven't taken the upper division quantum mechanics class yet, this weird thing of putting two descriptions between a vertical bar and an angle bracket, this is called Dirac notation. It's a way of describing a possible state of a quantum system, and it's in a combination of those two. The quantum mechanics of it you'll learn in fall. All you need to know right now is that people can prepare systems so that the two photons will always have opposite polarizations from each other. We don't know in advance which will be which, just that whatever one of them is, the other is the opposite. And then you could do an experiment. You could have a bunch of atoms here that have been prepared in such a way that they're going to emit like that. And then whenever you see something come through here, you see something reflected there. And whenever you see something come through here, you see something reflected there. And so you put a detector, and another detector, and another detector, and another detector. And you look and you verify that if this one goes off, so will this one. If this one goes off, so will this one. And those kinds of experiments are really important in quantum computation and quantum cryptography. And so those kinds of polarizers will be used for those types of things. Any questions?
In reality, is it really set up like that, or is it more of a linear combination of the two, where you have to check all the detectors and make sure that they're like orthogonal, if you know what I mean?
Oh, there's all sorts of things with the directions are always going to get more complicated. Any experimental geometry is always more elaborate than anything the theorist could describe in class. But the basic idea holds. Now, of course, what we need to do is I've said, hey, if we have something that transmits all of the TM light, getting something to transmit 100% of the TM light is easy. Getting it to reflect 100% or at least 99.999% of the TE light, that's hard. But in a different context, people worked that out. And that takes us to something called the distributed Bragg reflector. Here's the idea. The distributed Bragg reflector is just a whole bunch of alternating layers of two materials with two different refractive indices. N1, N2, N1, N2, N1, N2, N1, N2. And all of these layers are a quarter wavelength. Lambda over 4N1, lambda over 4N2, lambda over 4N1, lambda over 4N2, and so forth. By the way, this is the topic of your next project. And then doing this for polarized light is the topic of the last project before the final exam. Okay, so let's talk about what happens. We send in some light. Some of it gets reflected, some of it gets transmitted. Now, the reflected light, I don't know. I don't know whether let's say that this is N2 out here. This is going to work either way. Say that N1 is bigger than N2. Might be. Well, then we've got a half cycle phase shift here. All right. This first reflection got a half cycle phase shift. What about this thing that did a round trip? Did it get a phase shift there? N2, N1. N2, N1. Low, high, low, high. Did this round trip wave get a reflection phase shift?
Nope.
Nope, it did not. What was the phase shift that it got due to the round trip travel, due to the distance traveled?
Is it 2D N1 over the wavelength?
Yeah, okay, so 2dN1 and over the wavelength, and that's going to be equal to 2 times lambda over 4N1 times n1 over lambda. N1 cancels n1, lambda cancels lambda. We're left with half a cycle. So do these two interfere constructively or destructively?
Constructively.
Yep, because they both went through a half a cycle. Now, sometimes people think, wait, isn't a half cycle destructive interference? It's a half cycle difference that's destructive interference. Not a half cycle overall. The overall phase, it doesn't have to be, the overall phase doesn't have to be a full cycle or a half or 0 or whatever. It could be 7.32 cycles. And if the other one is 8.32, then they interfere constructively. And if the other one was 7.82, adding 0.5 or half a cycle, they interfere destructively. Okay, well, not all of the light gets reflected here. Some of the light goes through like that. Let's see. Does this light get a phase shift due to reflection right there?
Yes, by 1/2.
Okay, now what's the total phase? What's the phase shift due to the distance traveled? Quarter wave, quarter wave, quarter wave, quarter wave. Don't overthink it.
It's by half a phase.
Half?
Oh, wait, sorry.
Quarter plus a quarter plus a quarter plus a quarter. 1/4 plus 1/4 plus 1/4 plus 1/4.
Full cycle?
Full cycle. So 1.5. Now let's consider this. Goes through there, then goes back. Is there a reflection phase shift there?
No.
No, because it's in the medium N1, which is the high index medium. But a quarter plus a quarter plus a quarter, that's 3/4. Plus another quarter is 1 full cycle, plus another is 1.25, plus another is 1.5. Hey, all these things are interfering constructively. You see that? All of these things are interfering constructively. So these are excellent mirrors at a carefully chosen wavelength. And you might say, well, okay, fine, they're excellent mirrors at one wavelength. What about another wavelength? Well, sometimes you only want a particular wavelength, right? If you only want a particular wavelength, and there are a lot of important applications where people do, if you want something that will reflect just over a certain range of wavelengths, these are beautiful mirrors. These are amazing mirrors as long as you're targeting a very specific application. Now you could say, what if N2 was the high index and N1 was the low index? Well, let's see here. Then this would get a phase shift of 0. And this would get a phase shift of 1/2 right there, plus the 1/2 cycle phase shift. So we'd have a full cycle. This would get a phase shift. This would get a phase shift of 0. It would be a quarter plus a quarter plus a quarter plus a quarter. That's 1. This would get a phase shift of, let's see, N2 is the high index, so that would be 1/2 plus a quarter plus a quarter plus a quarter. That's 3/4 plus another quarter, 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 1.5 plus 1/2. So that would be 2. So no matter which way you stack it up, no matter whether you call the high index medium N1 or the low index medium N1, this idea works. If you just have a bunch of alternating quarter wave layers, then they will give you constructive interference of the reflected light. Any questions so far? What do you think you would do if instead of sending in this light on axis, we sent it in off axis? What do you think these layer thicknesses should be? Remember that our round trip phase shifts was always 2dn1, 2dn cosine theta. N will be whatever, n1, n2, n3, n whatever that layer is. Cosine theta of theta 1, theta 2, theta 3, whatever that layer is. All right. And so if we wanted this round trip to be a half a cycle, then D would be lambda over 4n cosine theta, because we just divide both sides by 2 and multiply by lambda, and then divide by n cosine theta. So with a small change, just a small little algebraic tweak, the idea still works for off-axis waves. Any questions so far? Let's talk about why people do this. Let's talk about what a laser really is. Well, actually, forget even that. We've got a mirror. A mirror. And what we call the active medium. Something that amplifies light. All right, basically something where if you have a bunch of atoms in their excited state, if a photon comes along and the energy of that photon happens to match the energy of the downward transition, then it emits a photon at the same frequency with the same energy. And now you've got two photons. This is basically resonance. It's like if you hit a tuning fork, get it vibrating, and then bring it near a string, and the string is at the same frequency that the string will vibrate at the same frequency as the tuning fork can vibrate at, then you get resonance. Well, this is basically, there's some important things I'm leaving out, but this is basically the same idea. And so if you have a bunch of atoms in their excited states sitting between two mirrors, then the photons that they emit just bounce back and forth and back and forth. And with each pass, they stimulate another atom to drop to the ground state. And when that atom drops to the ground state, then it too emits light at that frequency. And so now you got even more light bouncing back and forth. And it's all at the same frequency. It's all one pure note. And that's a laser. And this is a common way of making the mirrors for these lasers, all right? If the material is a semiconductor, semiconductors can be very good gain media, very good active media. You don't need them to be large like some big tabletop lasers you'll see. They can be very tiny. You have a thin layer of semiconductor, and the semiconductor has excited states and ground states, and electrons in excited states will drop to ground states, and you can use electricity to raise them to their excited states. You apply voltage and things will go to their excited states. And then you've got a bunch of layers, and this might be, it's actually not a wavelength, but basically the idea is that the round trip would be two wavelengths or one wavelength. The round trip phase shift could be a cycle or 2 cycles or 3 cycles or 4 cycles. You just put down different layers of basically other semiconductors. And oftentimes those semiconductors, it'll be another semiconductor with almost the same composition, just a slightly different chemical formula. And the nice is that if I think my dog is about to vomit. Bernardo, are you about to vomit? Bernardo, are you okay, little guy? Oh, you poor doggy. You poor doggy. All right, everyone. Let's take a 10-minute break. He just vomited. Okay, I'm back. I don't remember, what time did I stop at? I said 10 minutes at what time? 5:35, it looks like. Oh, perfect. I see you on the chat. Okay, yeah, I think he'll be all right. Just one of those things. But where were we? We were talking about distributed Bragg reflectors and a series of lambda over 4 layers. Now, if you go into the program that I posted on Blackboard, the Python file that we started using last week, you will see that under the test cases, there is there's test case 5, distributed Bragg reflector with a reflectance dip at 0.55 microns in normal incidence. So what this is a bunch of alternating layers of SiO2 and tantalum pentoxide. I should say that SiO2 and tantalum pentoxide are two things where I happen to have functions programmed for those. And so if you type in SiO2, Python knows, oh, that means that the refractive index I should use is whatever the refractive index of SiO2 is at this wavelength. And if you put Ta205 again, hey, whatever the refractive index of tantalum pentoxide is at that wavelength. Now, the mistake some people say is they're like, okay, well, I'll just put SiO2 in the denominator. I'll say that this layer thickness is 0.55 divided by 4 times SiO2. But we don't have materials who have a different thickness at every wavelength. It's not like this material can have one thickness when you send in 0.55 micron light and another thickness when you send in some other wavelength. I mean, there may be things that respond to light like that, but some sort of photomechanical effect or optomechanical effect, but those are unusual. All right, that is not the way that normal things work. So some people would always type into their code 0.55 over 4 SiO2 and then wonder what the hell's going on. You have to pick, you say, I'm going to design it for this wavelength. I'm going to make it so that the layer thickness is a quarter of this wavelength in the material. And then just accept that you send in any other wavelength and it'll still be that number of nanometers. You know, if a quarter of the wavelength, well, let's see here, 4 times that 0.55 divided by 4 times 1.4 something is going to be almost exactly 100 nanometers. So you just accept that, all right, I'm typing in the equivalent of 100 nanometers roughly. I send in some other wavelength, it still does a round trip of 200 nanometers. And if 200 nanometers is not a quarter of a wavelength, oh well, I get some other effect. Let's test this. So the way we test this, the way we change things is we comment out what we had previously as the definition of the coding layers. And we just uncomment this. And you have to uncomment all of the lines because it's a very long list. And then there's one special layer. There's one special layer that just for fun, I made it 2 times that. Let's undo that. Instead of 0.2 times 0.55, let's just make it 1 times 0.55. And then let's just run it and see what we get. And because there's a lot of layers here, it might take a moment to run. And it's probably not going to work right because I just realized that I didn't specify necessarily the correct mode. Let's do mode 0. Fix the angle of incidence, vary the wavelength. And this is designed for normal incidence, normal meaning head-on, 0 angle. So let's make the angle of incidence 0. Let's run it again. All right. And what we see is that at and around 0.55 microns, we do indeed get nearly perfect reflectance. It's not 100% reflectance because we don't have an infinite number of layers. There's always something that makes it through one and then the next and the next and the next and the next. And it's going to be a fraction of a fraction of a fraction of a fraction that makes it through. But still, it's very close to 100% reflectance. Then you might say, what on earth is going on down here? And the answer is that that function isn't reliable down there. So we're not going to worry about it too much. But this is indeed what I promised. It is something that produces very strong reflectance at and near a user-defined wavelength. Any questions on that? What you're going to do on the project is you're going to design one of these, and you're going to see what happens as we increase the number of layers. You're going to see, is it true that the transmittance, is it true or false that the transmittance decreases exponentially as the number of layers go up? Somebody want to give me a guess as to whether, I mean, it's clearly going to transmit less as the number of layers goes up, all right? But to say it decreases exponentially means that every time we add a certain number of layers, we multiply the reflectance by, every time I add a layer, I multiply the reflectance by the same number. And it's a number less than 1. So like if the transmittance of one layer was 0.99, then the transmittance of the next layer is 0.99. When we add another layer, it's 0.99 squared. When we add another layer, it's 0.99 cubed. When we add another, it's 0.99 to the fourth, and so forth. Whatever it is, the transmittance is decaying exponentially. Do you think that's true or false?
That should be true. I
Why?
think. Because at each layer, since it's obviously splitting into portions that's reflected and portions that are transmitted, at each layer, it's only transmitting a certain portion of the incoming light within that layer.
Yeah, so
And
you're
that
forgetting,
transmission shouldn't change because the angles will be the same for each layer because they're the same index of refraction, right?
so it's going to decrease exponentially because it's a fraction of a fraction of a fraction of a fraction. And so it's, if you basically, if I multiply something n times, then, you know, fraction of a fraction of a fraction of a fraction, if I multiply something n times, I've got that number raised to the power n. And you might say, well, hey, that's something to the power plus n instead of being something to the power minus n. But if that number that I'm multiplying is less than 1, then we could think of it as, you know, e, that the transmittance of one layer would be e to the minus something because it's less than 1. Well, 2 layers, e to the minus 2 something. 3 layers, e to the minus 3 something, and so forth. N layers, e to the minus n something, because you get a fraction of a fraction of a fraction of a fraction. Any questions on that? Here's a fun thing that happens.
Real quick, that would actually be exponential decay in terms of every other layer, right? Because we're repeating in
Sure. And
There's a
components,
choice.
all right? If you
Yeah.
think of the, like the components, since it's a repeating system, it's not the one material alone that's repeated. It's not the other material alone that's repeated. It's the combination of 2 materials. So a pair of layers, another pair, another pair, another pair. Well, let's see what happens if we change the thickness of the center layer. So you've got like this high reflectivity mirror, and then something a little bit thicker, and then another high reflectivity mirror. You got a bunch of quarter wave layers, which are like a mirror. It's a little bit wider, bunch of quarter wave layers. Now let's look at the reflectance spectrum. Ooh, what do you know? There's a dip in the reflectance spectrum. If we add this extra layer, there's a dip. And let's zoom in on this. And the way we're going to zoom in on it is we're going to look at a narrower range of wavelengths. So we're just going to look from 0.4 to 0.7. We'll do 2000 wavelengths. So we can see it more precisely. All right, there's definitely a dip there. Now let's watch what happens if I add more layers. There's a really easy way to add more layers. I'm just going to take all these things. What just happened? I'm going to take all these. Now I've doubled the size of the system. So each calculation takes longer, and I've doubled the number of wavelengths it's going to calculate. What do you know? That dip got narrower, a whole lot narrower. But it looks like we didn't sample the wavelengths finely enough. It's not at all obvious to me. You know, we're only going every so many nanometers here. Let's just see what happens. The easiest way to do this, to zoom in, is to go from 0.54 to 0.56 to really hit that range of wavelengths, to really look at it with fine precision. And you see that there's still a dip, and in fact, the dip is deeper. And now it looks like we've probably measured it pretty accurately. Now we've got something where actually it transmits quite a bit of light at that one wavelength and blocks all of the neighboring wavelengths. This is really useful. If you want to get very pure light, if we want to have a system where light is bouncing back and forth between the two mirrors, we've got one wavelength where it can bounce back and forth between the two mirrors and still get through. And you may be thinking, but wait, don't we want high reflectivity? Yeah, we want high reflectivity, but we also need the light to get through in the end as a laser. This is what's called a special cavity mode. And to see what's really going on here, I'm going to have it plot the field. It's going to take a while, but all right. So again, we've got our very sharp dip. And then let's look at what the system really is. All right, we've got alternating refractive indices. And then we've got this wider region in the middle. And in that wider region, we have a much stronger field, right? So we've got light confined in there. Any questions? See what would happen. I made the left side glass and the right side air. Let's just see what would happen if we made it more symmetric. Doesn't change much. Still the same basic principle. What we've got here is a device that does something kind of neat. It can transmit light at one specified wavelength. Not perfectly transmit, but transmit pretty well light at one specified wavelength. So if you want a filter, you've got a filter. But it does so much more than that. It confines that wavelength to the center of this device. So if you want that filtered light to do something, to interact strongly with something, you would put whatever you wanted to interact strongly with right there in the middle. Any questions? No questions? This is the basis for a lot of optical devices used today. This is the basis for most semiconductor lasers that are used in telecommunications. It's the basis for, frankly, a lot of solid state lasers used as toys. It's the basis for a lot of the devices used for filtering and manipulating light in telecommunications. So it's pretty important stuff. A good source for learning about this is Joe Anopoulos' book. Just Google for Joe Anopoulos. Any spelling will do, but Joe Anopoulos, Photonic Crystals. John Joe Anopoulos, Photonic Crystals. And there's a free PDF of his book available. I will drop that in the chat. It's called Photonic Crystals because, well, it's photonic, it manipulates photons, light, and it's a crystal because it's periodic. Now, one thing that people do with stuff like this, another thing besides telecommunications and lasers, is I posted on Blackboard some stuff from Semrock, a company that makes filters for use in labs. It's worth spending a few minutes looking at some of their figures. They do more than just lambda over 4 layers. It's not always about lambda over 4 layers. There are other tricks to use. What I want you to take away right now is that the lambda over 4 layers are common, they're useful, and you can use them to engineer so that there's a range of wavelengths that is weakly transmitted or strongly reflected. But people have found ways to do so much more. People have found ways to engineer filters that have much less messy transmission and reflectance spectra. And they do it using mostly sometimes patented, sometimes trade secret techniques. But you can design, this would be like an ideal target. You can design something like this, which yes, is really messy at these shorter wavelengths, so you wouldn't want to work there. But at these longer wavelengths, look, you've got a range where you get almost 0 transmission. And you have a range where you get almost perfect transmission. And so it could be very good if you needed selection where a whole bunch of things just above a threshold get through and a whole bunch of things just below a threshold don't. They can make something that transmits at one specified wavelength, like I just did. And a lot of this, again, is either patented or trade secrets, but they can engineer these kinds of, these are called notch filters because they basically notch out certain ranges that will get transmitted and certain other wavelengths, certain other ranges that won't. Any questions? There's a lot of elegant physics to be studied in here when you have waves resonating back and forth. There's a lot of very interesting one-dimensional physics problems that can be done. And although we're behind, I want to at least spend a little bit of time telling you the tricks behind how these things are designed, because there's a lot more elegant wave physics that you can study with this. We do this, the code I wrote does something called a transfer matrix calculation. The way the transfer matrix works, say we have a system of many, many layers. I'm not making any assumptions about which ones are high index, which are low. They could all have different indices for all I know. But let's say that I send in some light here.
Dr. Small, if you're drawing, you have to change your sharing screen.
I thought I was. You're not seeing this?
We're still seeing the multi-notch PDF.
Oh no, from my screen it's good.
Yeah, I still see him, or I see him doing the transfer matrix calculation.
Oh, that's odd. No, I think I will exit and come back then. It's probably my end.
That is very weird. So it might be that you have to select that you're seeing both of the shared screens, whereas some of you are set up to just see the default shared screen. You seeing it now, Diego?
No, my Zoom appears to be bugged. Like I can't even leave the meeting.
Okay, well, this will be showing up on the recording, so I'm going to continue, and whatever you, I'm going to post the notes after class, and the notes will also be visible on the recording on YouTube.
That's fine. I'll rejoin right now. Command center this.
Okay, so if we send in light here, we don't know how much will be transmitted, how much will be reflected. But here's what we do know. We do know that all of the light on the far right side of the system is only going to the right. And in each layer, we could say that the electric field is equal to EJ plus, where J is the layer number, e to the I n sub j k naught x plus EJ minus e to the minus I n sub j k naught x, and I should have an e to the minus I omega t here. All right, that's what we know. We know that in any layer, there's going to be a wave going to the right and a wave going to the left. And so in each layer, we could represent the field with, assuming that all of the indices are already known, we've got that information stored away somewhere. We have complete knowledge of the field in that layer just by specifying EJ plus and EJ minus. We know these two coefficients, then we know everything that we need in order to calculate the field in that layer. Now, if all I said is, hey, we just need two numbers, well, that doesn't end the problem. But I've already taken it down to recognizing that only two numbers matter in each layer. Each layer can be specified with two things. And furthermore, the field is continuous across a boundary. So if this is layer J and this is layer J plus 1, then I know, and this is xj, which is the location of the interface. E is continuous, and dE dx is continuous. So that means that EJ plus e to the I nj k naught xj plus EJ minus e to the minus I nj k naught xj equals EJ plus 1 plus e to the I nj plus 1 k naught xj. Now you have to be a little bit careful. I'm saying xj, meaning that I have decided that I'm naming this interface after the thing on the left rather than the thing on the right. So we don't put xj plus 1 up here. We decide we're going to name that interface. And once we name that interface, both sides have to use the same name. E minus j plus 1, e to the minus I n j plus 1 k naught xj. All right. And then we have a similar condition with the derivatives. I k naught nj ej plus e to the I yada yada minus ej minus e to the minus I yada yada equals I k naught nj plus 1 times ej plus 1 plus e to the I yada yada plus ej plus 1 minus e to the minus I yada yada. Okay, so I've got these equations. I've got two equations and two unknowns. We're going to say that the field in layer J plus 1 is given. or known. Now we're used to saying, okay, well, we start at the beginning and then we try to figure out the next thing. So it's kind of counterintuitive to say, hey, we're going to start at the far right, the thing with the highest number. We don't normally call that the beginning, but we can call that the beginning. A downward trip starts on the top floor. So, we're going to call this the known. And you're going to say, well, how do we know that? Well, here's what we know. We know that over here, En plus is 1. And En minus is 0. Okay? Somebody measures a field over here. And they measure a field with amplitude 1. You're saying, wait, did they? Sure, let's assume that. Let's assume someone's done the measurement. You're saying, but how do we know they got a field with amplitude 1? That would mean that it might have been a really huge field over here. Yes, it might have meant that. But one way or another, somebody measures the field over here and it has amplitude 1. And it's all going to the right. So we immediately could work out what the field right here, just on the other side of the interface, must be. And then once we know the field over here, we can work out the field over there, because we would work out what these two coefficients are, these two left coefficients, the two coefficients in this layer, solve for these. And once I've got those, I can calculate the field over there. And hey, now I've got the field over here. And we already just figured out that with an interface, well, at an interface, we've got two linear equations and two unknowns. So I could then calculate the field over here. And once I got the two coefficients over here, I could plug in a different coordinate and find the field over here. And once I find the field over here, well, again, solve two equations and two unknowns. Questions on that idea so far? It gets even better. Because these are linear equations, I can say that EJ plus EJ minus, that process of solving for these can be done in terms of matrices. And I'm not going to write out all the matrix elements. We're definitely behind the class. But I could write out all the matrix. I could write out all the matrix elements. We could solve for them. And I'm just going to call this, some books call it D. The interface matrix. And then the process of going from, say, here to there, or here to there, or here to there. Well, there's a matrix for that. It's an easier matrix. These are on the right side of the layer. These are like right over here. If I want to get to there, those were coming from the left side of the other layer. They were over here instead of over there. And that it's a bunch of phase factors, okay? To move something, as something goes from left to right, as a wave propagates, it just gets a phase shift. So figuring out what the wave over here is in terms of the wave over here, if it's not going across a boundary, if it's just going through a uniform medium, well, that's just multiplying by a phase factor. This is a really easy matrix to multiply. So I've got two matrices, interface matrices and phase matrices. And I just start over here where I know that one of my things is 1 and the other variable is 0. I multiply by a matrix and I get across the interface. I multiply by another matrix and I get through the layer. I multiply by another matrix, I get across the interface. I multiply by another matrix, I get through the layer. I multiply by another matrix, I get across the interface. I multiply by another matrix, I get across the layer. And I just keep doing that and doing that and doing that over and over and over again until I get to here. And once I get to here, now we know the incident and reflected fields. And that is how I figure out how strongly a system reflects or transmits, given information on all the layer thicknesses and all the refractive indices and what the wavelength is. And that's what my code does. My code just multiplies a bunch of 2x2 matrices over and over and over again. Any questions? I did not invent this. The transfer matrix method has been around for a long time. I have no idea who invented it, but I know that it is in the most holy Bible of optics, Principles of Optics by Born and Wolf. It's actually in chapter 1 of Born and Wolf. Thanks be to God. In chapter 1 of Born and Wolf, they discuss this, and that's because it is really important. Any questions? Multiplying 2x2 matrices is almost as easy as a numerical calculation can get. And that's why I wrote my own code, but I would not write my own Zmax. For thin films, I can write my own. It's about as simple as numerical work can get. Writing your own Zmax, even just for the geometrical optics, the ray optics, the ray tracing, you're solving nonlinear equations, nonlinear algebraic equations. They're not the hardest nonlinear algebraic equations ever, but still, for each little detail, the processor time that you're going to use is bigger than the processor time that you would have to use for just doing some linear operations, because you're going to be solving a bunch of, to use Snell's law, you're gonna have to solve some inverse sine problems. You're gonna have to do some arc sines. Those take some processor time to evaluate. Maybe thinking, well, they don't take that much time on a modern computer. No, not that much time on a modern computer, but more processor time than just a couple of multiplications. There's many more multiplications than that. Not to mention figuring out with these complicated shapes, where does it hit? Again, you're going to be solving some nonlinear algebraic equations. Doesn't take that long on a modern computer, but still takes longer than a couple of multiplications and additions. Any other questions on this? This is as far as I'm going to go with thin films in this class. Your next projects are to basically study distributed Bragg reflectors in different conditions. Just model distributed Bragg reflectors in the Python program. First, for trying to get high reflectance of a chosen wavelength and verifying certain patterns. Then setting things up so that all the waves are incident at the Brewster angle and trying to see what happens then. You know, the TE and TM reflectances should look very, very different.
Professor.
oh.
Go ahead. Sorry.
Oh, okay. At the bottom for the matrix on the right side of the equal sign, in the top left where it says e to the negative I n j, is it a plus or minus?
That should be a minus.
Or minus? Okay.
Pretty sure it should be a minus.
Professor, I have a question. So for when calculating the transmittance of the DBR layers, we would apply this, or that's for like the next week.
You're not writing down any of these matrices, Kenneth. This is what my code does. You just tell it, I want something with these layers, and the code multiplies these matrices.
Yeah. Okay. But okay. Yeah, I think, okay.
I was showing you this not because I expect you to go out and write your own code for this. I was showing you this simply so that the code is not some magical black box that you look at and say, well, I press a button and the magical thing works, and then it outputs an answer, and that answer was decreed from on high by the guy in charge. I want you to know what is the algorithm that the code is using. And also, some of the ideas behind this, you might never write a thin film solver in your life. But some of the ideas that you find a problem and you recognize that you can break it into steps, and there's a very simple operation that goes from one step to the next, to the next, to the next. That's an idea that might turn out to be useful in other contexts, or understanding why this is something that I could write on my own and Zemax isn't. Well, it's because multiplying matrices is easy. All right, it doesn't take all that much time for a computer to do it. On the other hand, evaluating a whole bunch of inverse signs, that's a little bit harder. And looking at curved shapes and figuring out, okay, so we've got our optic axis and we've got this curved glass, and this ray hits here, and this other ray hits there, and these are two different x coordinates. Let's think about the kind of algebra we would need to do in order to get the actual number, to say, what is the x coordinate here? What is the x coordinate there? And we better be able, you might say, well, can we make an approximation? No, that's not what Zemax does. I mean, technically everything's an approximation because you can only go to so many decimal places. But Zemax is trying to be way more precise than like doing a Taylor series or something. So you'd have to do some algebra that really can't be done by hand. So it would be done by trial and error to see how close can you get it. And you better be able to get it to many decimal places. All right. Whereas multiplying matrices is a much more straightforward operation. And so that is why I can write my own thin film solver, but I can't write my own Zemax on the fly. Other questions? By the way, here's why I can't write my own Zemax was not meant as oh, here's why I can't do this. It was meant as here is why certain computational tasks are hard. Here's why certain computational tasks are easy. Think about what category a given problem is in. That might tell you, can you do it yourself? Should you call a pro? That might tell you, if I'm going to do it myself, should I try to use this kind of algorithm that fits into the easy category, or that kind of algorithm that fits into the not so easy category? All right. In the time we have remaining, we're going to start talking about diffraction gratings, and we'll have to finish them on Tuesday. Now you should be seeing a picture of a bunch of different line spectra. A diffraction grating is something that we use to split light up into many different wavelengths. So the whole idea of a diffraction gradient is that you got a bunch of evenly spaced slits and light hits it and different wavelengths come out at different angles. And this is the fundamental basis for almost any statement we can make where we say, oh, well, we have this much of this wavelength and that much of that wavelength. Or, oh, we know that this material emits at this wavelength, but not at that wavelength. Or, oh, the transmittance is high at this wavelength and low at that wavelength. Because somebody took the light that's coming in or going out and sent it into a device like this. And then different colors got sent off at different angles. And depending on which angle it got sent in at, you could say, all right, well, depending on which angle it got sent out at, you could say, oh, it's this wavelength or that wavelength. And here are line spectra of different elements. There's some background here, but here are the more intense lines. And what you do is you would basically have the lights coming out, and at each of these positions, you'd have a different detector. You know, the electronic detectors that people can make are going to be a few tens of microns across. So you could have a whole bunch of them, just like the sensors on a camera. You just basically, in effect, you could aim it at a camera, right? Except that, you know, you only need 1D instead of 2D, but it would basically be aiming it at a camera. And depending on which pixel the light hits, you now know what wavelength you have. And so if this pixel is really bright and this other pixel isn't, then you say, okay, I got a whole bunch of light at whatever wavelength was aimed at this pixel and not so much light at whatever wavelength was aimed at that pixel. That's the idea of a diffraction gradient. That's why it's important. It's the foundation of almost any statement we make about what light is made out of. Any questions so far? It's not the only way, I should emphasize. There are other ways to make a spectrometer, but it is a very, very common and important way. And so it's worth studying. The most basic formula of a diffraction grating is really easy to specify and derive. Okay, the most basic formula is one that you've probably seen before. It's just d sine theta equals m lambda. I'll explain that. So let's imagine we've got a bunch of slits and the spacings between the centers are d. They're all the same. They're periodic. And over here, we've got a detector. And on that detector, we've got a whole bunch of little pixels. And I want to know how much light is hitting this pixel. So we're just adding up the waves from each of those slits. Just adding up a whole bunch of waves. And of course, these lines aren't perfectly parallel to each other, but let's pretend that they're parallel, because in reality, it's not like all of these distances are comparable. In a real device, like say the spectrometer is used in the 2540 labs, this might be a centimeter, and this might be less than a millimeter at most. And this will be like maybe 500 nanometers. I should know the exact number, but I don't have it memorized, but it's going to be small. all right? It's going to be hundreds of nanometers. And so this distance here, the horizontal distance is huge. All the vertical distances are small. So these paths are nearly parallel. All right, well, we can do what we usually do. We can figure out if they're nearly parallel, then all of the path difference is there, this little distance delta. This is theta. So this here is 90 minus theta. This up here is theta. D is the hypotenuse, so I'm going to sketch it out down here, exaggerated. It's not even that much exaggerated, just separate out from the busyness of all the other lines. Got a right triangle, delta is d sine theta. Any questions so far? All right, so delta is d sine theta, and if d sine theta equals an integer times lambda, then these two, the waves from these two slits will differ by 1 cycle. And the waves from this and this will differ by 2 cycles. And this will differ by 3 cycles. If we compare with here, it's 4 cycles. If we compare with there, it's 5 cycles. And if 2 waves differ by an integer number of cycles, everything interferes constructively. So we should get a huge signal over here. If we were to plot intensity, we would have a huge intensity there. Now we could ask, any questions on that reasoning so far? Now we could ask, what if we were looking somewhere else? We're looking at any other pixel, any other detector, right? Well, in general, the field will be the sum over all of the slits, number them with j, e to the I times k delta, right? Because they all have, we're assuming they all have the same amplitude. And so the phase is just going to be k times delta times j. If this is j equals 0, this is j equals 1, j equals 2, e to the I times k times delta times j, right? So we'll measure everything with respect to, say, down here. This one is in phase with itself. The difference is 0. This one is, well, the path difference is delta. And so the phase difference is k times delta. This one, the path difference is 2 delta. So our phase difference is equal to 2k delta. Here it's 3 delta. There it's 4 delta. There it's 5 delta. There it's 6 delta. All right? And so we've got, we're just adding up this thing. Now, in order to add up a whole bunch of complex numbers, I'm going to write this as the sum of e to the I phi times j. Phi is just equal to k delta. I'm writing it that way because I want us to think of it like an angle, because of course it is. Complex numbers exist in a complex plane. Living in this complex plane, you know, we could say, well, one of those complex numbers is this. Let's see if I can draw a nice unit circle. And then I will now. I make one more attempt at artistry, and then I'm just going to say, screw it, we have to move on. More or less artistic. Okay, so you know, one of them's over here, and then the one that has twice the phase, so 2k delta will be there, 3k delta, and if we add up enough of these are all evenly spaced. Pretend that I drew this to scale. So they're all just a bunch of arrows in the complex plane. Each of these phases is just an arrow in the complex plane. What do you think they add up to?
Do they not just cancel out?
What?
Do they cancel out?
Yep, they cancel out. They add to 0. Now we could prove this rigorously. If I have n slits and k delta, which is equal to k d sine theta, if this was all done rigorously, if I have n slits and k delta was 2 pi over n times an integer, then I can prove rigorously that they exactly cancel. But what if n is like 1,000? Okay, and k delta is 2 pi over 1,000 multiplied by, well, 3.1, okay? Then I will have a little bit of a leftover, okay? I'll have a little bit left over. When I'd have to add go around a few times, I'd have a few left over. I'd go around 3 times and then a little more. So when I add up all 1,000 of them, I go around 3 times and then a little more. I'd have a few extra. So I have a little bit of a field, okay? If I'm up here, where I've got constructive interference of all of them, E equals 1,000. E squared equals 1,000,000, 10 to the 6th. But then over here, KD sine theta equals 2 pi over 1,000 times 3.1. If I try to do it in my head, I'm going to get it wrong, but I've got some very small fraction. I've got maybe 100 of these. Let's say, just for the sake of argument, I get 100 of them, okay? I've got 100 extra fields. Well, 100 squared is 10,000. Comparing that intensity, 10,000, with 10 to the 6, clearly the field over here is weak and the field over here is strong. And this is why when you send light through a diffraction grating, you just see a handful of bright spots. You get a bright spot if d sine theta is an integer multiple of lambda. D sine theta equals m lambda is equivalent to kd sine theta equals 2 pi m, because k is 2 pi over lambda. And so we've got 2 pi d sine theta over lambda equals 2 pi m. The 2 pi's cancel. D sine theta is m lambda. Okay? So what I want you to take away at this point is that, first of all, if they're all in phase, well, of course, you get constructive interference. And if they're out of phase, if they're not all in phase, then unless those phase differences are really, really small, we are going to get that it has gone around. We're going to get something that cancels out almost perfectly. All right, because the number of trips is going to be equal to, let's see here, nk delta over 2 pi. Each phase angle is k delta, all right, n phi, all right? Each phase angle, each little one gets displaced by an angle phi. So here's phi, here's 2 phi, here's 3 phi, here's 4 phi, okay? And so after we've gone around, after we've added up n of these, our angle is n phi. And so the number of trips will be n phi over 2 pi, because one trip would be 2 pi, all right? Well, we get cancellation. We're going to get strong cancellation if n phi over 2 pi is bigger than 1. Now, if it's way less than 1, imagine a scenario where I just add up a handful of these. My first one, my second one, my third one, my fourth one. All right, they only add up in this range. Do they all add up perfectly? No, but they still add up to something that's pretty large. So they cancel if n phi, oh, I should rewrite that. N phi over 2 pi minus the nearest integer is about 0.5. All right. So let's say that for the wavelength that for some chosen wavelength, we set this up so that we're looking at the pixel where lambda is really bright. We're looking at this pixel where one particular wavelength is really bright. For some chosen wavelength, d sine theta equals m lambda. Some carefully chosen, but for a different theta, we just look a little ways away, d sine theta plus delta sine theta equals m plus 1/2 lambda. All right. M plus 1/2n lambda. So that phi, the change in phi, differs from 2 pi times an integer over n by pi. Or n phi differs from 2 pi times an integer by pi, all right? So n delta sine theta times d flat. All right, I'm going to make one last point, and then I'm going to show you a graph that I'm not trying to take more time. I'm going to try one more time to state this correctly. Then I'm going to show you a graph that'll hopefully bring some physical sense to this, and then we'll end on that note. All right. What am I trying to say? N phi, which is n times kd sine theta plus delta sine theta. I'll write a sine theta naught, the one that we're looking at, equals pi. N times 2 pi over lambda pi plus 2 pi times an integer. What does this mean? This means if we add up all of those angles, this is what we get from, this is what we would get if we were at the one that we know gives constructive interference. This is our extra. This is what we would get if we had constructive interference. These cancel. All right. If extra equals pi, or n times 2 times d delta sine theta equals 1, or delta equals lambda, the change in sine theta is lambda over 2n d. All that means is we can figure out how much you'd have to change the angle before the thing goes to 0. What on earth does all of that mean? I think the best way to make some sense of it, already being over time and hearing a sick dog bark, is to show you one graph, and then I will call it a day. Here's a mathematical file that actually calculates the intensity of the light at different angles.
Can you change your screen?
Oh. Here's a mathematical file that shows you the intensity of the light at different angles. I'm just going to zoom in on one of them around 50 degrees. So I'm going to go from 50 to 55. And you see how there's a big peak and then it quickly decays. And next time we'll figure out just how wide this is, just how far off you can go before it decays, and how that depends on the wavelength and the angle and the number of slits. And I'm sorry for keeping you over. Any questions? All right, have a good weekend. Okay, Adrian, you can let him out and I will take care of him. So I will cuddle them. Throw up on me, so be it. I mean, I'm not telling you to do it. I'm just saying that I'll love you anyway if you do it. Let's go upstairs. You poor sick doggy.